behavior of things on a small scale is so fantastic. It's so wonderfully different, so marvelously different than anything that behaves on a large scale. You say electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly.
Subatomic particles can disappear and reappear in another place. And they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places it can disappear and reappear include specific locations around the nucleus. And that makes it look like a shell. Basic particles can also be in more than one place at a time if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. All this jumping around makes particle description so inexact. But then existence itself is inexact at these tiny scales. The question is often asked, what is it that is waving when a particle is described as a wave? And after a lot of hem-hawing around the issue, the right answer is, existence is waving. The particle is jumping around, coming into and out of existence. And those places where the wave crests are maximum are the places where the particle materializes, most of the time. While the places where the crests are minimum are the places the particle avoids. The wave is a map of the particle's existence. And as the wave changes, the particle changes as well. Schrödinger's quantum mechanics explains every element in the periodic table of the elements. The solution to Schrödinger's equation, called the wave function, is a fantastically accurate description of the real world. Without going into too much detail, let's look at a proton and an electron. Since the electron has a very tiny mass, it can occupy a very large region of space. Conversely, the proton has a very large mass, 2,000 times that of an electron, and therefore it occupies a very tiny region of space. The result is a quantum mechanical hydrogen atom, a tiny massive nucleus surrounded by a much larger cloud representing the electron. If we look at a simple graph relating the probability of finding the electron in a shell at a given distance from the nucleus, we find that as we travel outward from the nucleus, the probability increases at first as the shell expands. It reaches a maximum value and then decreases again as the electron cloud thins to almost nothing at large distances. Amazingly, the radius where the probability reaches a maximum is precisely equal to the radius of the first allowed orbit of Niels Bohr's model of the hydrogen atom. And its energy is exactly equal to the energy of an electron in this orbit in the Bohr atom. So this is a very good picture of a hydrogen atom with an electron in the lowest energy state. The electron occupies a cloud instead of an orbit. but it spends most of its time at the radius predicted as an orbit by the Bohr model. It also spends most of its time possessing the energy that an electron in that orbit would have. But of course, the atom is not always found in the lowest energy state, as there are other orbits allowed in Bohr's model. There are other higher energy states in the quantum mechanical hydrogen atom. These states are defined primarily by the quantum number n that we talked about earlier. And for each state, the electron has a different energy, which results from the shape of the electron cloud. For n equals 1, called the ground state, the shape is a symmetric cloud, the same in all directions. For n equals 2, the shape can take two forms, although both shapes have the same energy. One is a double spherical cloud, one sphere inside the other, while the other shape for n equals 2 is in the shape of a dumbbell. For other values of n, the shapes can be pretty strange, like this torus plus dumbbell shape. An electron in the lowest energy shell in an atom can be struck by and absorb the energy of a photon, giving it enough energy to jump to the next energy shell. And the reverse process allows the electron to jump back down into the lowest energy shell and emit a photon. The color of the photon depends on the energy difference between the two shells. We have just discussed how Schrödinger's equation shows us how to accurately describe fundamental particles with a wave function. Now let's examine why two electrons together reveal a feature of quantum mechanics totally unlike anything in the large-scale world we inhabit. In a classical setting, even if two things are identical, they are still individuals. As long as we keep track of them carefully, we can treat them separately and label them A and B, or X and Y, or 1 and 2. But consider what is different about a two-electron system. Whether in an atom or in a box, it doesn't matter. Since the two electrons are consistently phasing in and out of existence, and since they are absolutely identical, it is impossible to keep track of specific individuals. Because of this, we must use a combined wave function to describe the pair rather than using two individual wave functions. This new two-particle wave function will have two parts to it, and those parts will either add or subtract. Physicists would say this makes the wave function either symmetric or antisymmetric. And it turns out that only the antisymmetric function works for the electrons, and quarks, and protons, and neutrons. Let's let this red wave represent the first part of the combined wave function, and this green wave represent the negative of the second part. If the electrons are in the same state, these two waves will be a mirror image of one another. As one goes up, the other goes down in perfect synchrony. So when we combine them, we get no wave at all. And since the wave is a map of electrons existing at that point, no wave means no electrons. So clearly, two electrons can never be in the same state because that causes their combined wave function to disappear. Now the only components making up the dynamical state in the atom is the shell it occupies. and another property that electrons have called spin. You can think of electrons as little spinning tops if that helps. And these electron tops can spin in only two ways: upright or upside down, which can make them distinguishable. So the end result is that two and only two electrons can occupy each shell in an atom, one with spin up and the other with spin down. Other electrons in the atom must occupy higher and higher shells. This is called the Pauli exclusion principle, first espoused by Wolfgang Pauli. Without this exclusion, all electrons would occupy the lowest energy state, and atoms would behave very differently, and the universe would be a very different place. As we take apart matter down to the smallest scales, we must pass through levels of structure that are only possible because of forces that hold these structures together. The proton and electron, for example, are attracted to each other, and that force of attraction is what holds them together in the atom. But what is it really that causes this attraction? How does the electron know the proton is there? And what draws it towards the proton? How does the electron know not to be attracted to the neutron? The answer is that the electron and the proton each fill the space around them with countless millions of other tiny particles that have only the most ephemeral existence. Because it is electrically neutral, the neutron does not. These particles come into existence only briefly and are gone, only to be replaced by another one thrown out by the parent particle. On this scale, the tiny bit of energy that is needed for the existence can be created out of nothing. But they also must disappear in the briefest instant, because the energy used to create them can only exist for a very brief instant. You can imagine these virtual particles as balls tethered to the parent particle by a rubber band and snapping back to the parent when they disappear. If one or more of them should encroach upon the territory of a virtual particle tethered to another parent particle, they can get entwined and exchanged. Such an exchange is felt by the parent particle as a force. Scientists recognize 4 distinct kinds of force fields, and they all work through the mechanisms described above. You are readily familiar with 2 of these forces: gravity and electromagnetism operate on a scale that we encounter in our everyday life. A third force causes quarks to stick together in protons and neutrons, and a residuum of this force causes protons and neutrons to stick together in the nucleus of atoms. This force is called the strong force, or sometimes the color force. The fourth force causes radioactivity and is called the weak force. The virtual particles that make up these fields and get exchanged in each force are called gauge bosons. And each of the 4 forces has its own gauge boson. Within limitations, energy and mass can be created out of the nothingness of space-time, but only for a very brief instant. And the more energy and mass these virtual particles have, the shorter must be the time that they can exist before snapping back to the parent. Lighter gauge bosons can exist for a longer time, and these in turn can get further from the parent before they must return. So the range of a force is directly related to the mass of its gauge boson. The photon is a gauge boson for the electromagnetic force, and the graviton is the gauge particle for gravity. Both of these particles are massless, and so the range of these two forces is unlimited. So let's turn our attention to the interaction of light and electrons. We can apply the every path method here as well. We start by drawing diagrams of every possible path for an interaction to occur. And surprisingly, we can reduce the task of making these diagrams to just 3 fundamental actions that we need consider. Every possible interaction diagram can be reduced to combinations of these 3. 1. A photon goes from place to place. 2. An electron goes from place to place. 3. An electron emits or absorbs a photon. Each of these basic actions has an amplitude, an arrow, that can be calculated according to certain rules. Let's draw a diagram of one action. A photon goes from place to place. We put time on the vertical axis and space on the horizontal axis, and we will represent the photon by a wiggly line. So basic action 1 looks like this. There is a certain probability amplitude for the photon to go from A to B. Let's call it P, A to B. And there is a formula for the size of the corresponding arrow. In the second basic action, an electron goes from point A to point B. Let's call the amplitude for this action E, A to B. Notice electrons are represented as straight lines. The formula for the amplitude of this action includes a very special number called n. And it's interesting to note that the formula for P, A to B, a photon going from point A to point B, is the same as E, A to B, an electron going from point A to point B, if n is set to 0. The third basic action is an electron emits or absorbs a photon. This action is called a coupling. Every coupling is a junction between 2 straight lines and a wavy line. There is no complicated formula for the amplitude of coupling. It is just a number, and we call it J. Its value is about negative 0.1. Now let's calculate the probability that 2 electrons at 2 points, 1 and 2, end up at points 3 and 4. This event could happen in 2 ways. The electron at point 1 could go to 3, given an amplitude of E 1 to 3. And the electron at 2 goes to 4, giving E 2 to 4. So the overall amplitude for this path is E 1 to 3 times E 2 to 4. Another way would have electron 1 go to 4 and electron 2 go to 3. This would have an amplitude of E 1 to 4 times E 2 to 3. And of course, the final step is to add these 2 arrows to get the total amplitude. This would be a good first approximation, but we should also consider other ways this event could happen. For each of the ways we just described, one electron could emit a photon on the way, and the other electron could absorb a photon along the way. Calculating this complicated amplitude involves the number J we mentioned earlier. It is shown here. And there are more possibilities. This looks hopeless, but the number J will come to our rescue. The first ways this event could happen have no J's in the calculation. The next way had J times J. And the last would have J times J times J times J. And since J times J is less than 0.01, the arrow from this possibility is only 1% as long as the arrow for the first way. And the J times J times J times J path is less than 1/10,000th as long as the no J method. So you only have to go to the more complicated possibilities if you need increased accuracy. When an electron is placed in an external magnetic field, it exhibits a response called its magnetic moment. The diagram for the first approximation of the magnetic moment of an electron is very simple. An electron goes from place to place and couples with a photon from a magnet. This gives a value of 1 for the magnetic moment. After some years, it was discovered that the value was not exactly 1, but something like 1.00116. In 1948, the first second-order corrections were made. They involved J times J terms from diagrams like this. To calculate the contributions from this class of diagrams, we had to make an arrow for every place in space-time that the photon could be emitted and every place that it could be absorbed. And since then, experiments have measured the magnetic moment to even greater accuracy. So now we needed to consider all the ways the electron can go from place to place with 4 extra couplings. It took 2 groups of physicists 2 years to calculate these terms. The term with 6 extra J's involves even more possible ways the event could happen. It took 20 more years to get this extra accuracy figured into the theoretical value of the magnetic moment. With better computers, more and more J's have been added. And theory and experiment now agree in more than 16 decimal places. Quantum electrodynamics is perhaps the single most successful physical theory ever devised. It forms the bedrock foundations for all of today's unification theories, like the Standard Model. QED, Quod erat demonstrandum.